In this video, we'll look at catalytic hydrogenation. This reaction is often simply referred to as hydrogenation, and it represents the addition of hydrogen to an organic compound. During hydrogenation, a catalyst must be present. So this is where the catalytic portion comes from. The catalyst that you will see with the hydrogenation reaction can either be platinum, palladium, or nickel. So any of those metals. Here I have platinum shown. And so when drawing the product of a hydrogenation reaction, especially if you are dealing with a skeletal structure, it is as easy as simply redrawing the compound without that double bond. Because recall, in skeletal structures, during the skeletal structure you see the bonds between the atoms, but you do not see the bonds between carbon and hydrogen. So if we look at where the double bond was located, so carbon 1 has 2 bonds. We know that carbon always wants 4 bonds. So since it has 2 bonds, there are 2 that we do not see, which would indicate carbon 1 has 2 hydrogen. Carbon 2, we can see 3 bonds. So that means that there is 1 bond that we do not see. So therefore, carbon 2 has 1 hydrogen. During the addition reaction, when organic compounds react, old bonds break so that new bonds can form. So when that old bond broke, and in this case we have a nonpolar compound, only carbon-carbon and carbon-hydrogen bonds, so we don't have an uneven distribution of electrons. However, this double bond becomes more reactive compared to the single bonds that are present between other carbon atoms. So that double bond being more reactive is going to be the old bond to break. When that old bond breaks, that means that we no longer have the double bond present. If you're dealing with skeletal structures, you're finished. How do we know we're finished? Look back at carbon 1. Now carbon 1, there's only 1 bond. So that means that this carbon has 3 bonds that are not seen, so it has 3 hydrogen. Carbon 2 has 2 bonds. So now we have 2 bonds that are not seen, so it has 2 hydrogen. So we've gone from 1 hydrogen on carbon 2 to 2 hydrogen. We've gone from 2 hydrogen on carbon 1 to 3 hydrogen. So this H2 molecule, and remember hydrogen is a diatomic molecule, we've added 2 hydrogen to this compound. So we've gone from an alkene to an alkane. Not only did we look at an addition reaction, hydrogenation also represents reduction. Because recall that during redox reactions involving organic compounds, we can look at a change in the number of hydrogen and or oxygen atoms. In this case, we don't have any oxygen. But if we go through and we look at the hydrogen, so we could have also figured out the hydrogen on these other carbon atoms as well, but they didn't change. So really what we were concerned about is the fact that we saw an increase. But I'll still go ahead and show this carbon has 2 hydrogen, this carbon has 2 hydrogen, this carbon has 3 hydrogen. Same thing here. That same carbon number had 2 hydrogen, 2 hydrogen, 3 hydrogen. So if we go through and we add up all the carbon and hydrogen atoms in the alkene, there were a total of 5 carbon. If you go through and add up all your hydrogen, you have 10 hydrogen. Do the same thing with the alkane. 5 carbon, go through and add up all your hydrogen, you have 12 hydrogen. So going from this alkene to the alkane, we saw an increase in the number of hydrogen. Increase in hydrogen represents reduction. So hydrogenation represents an addition of hydrogen. So it's an alkene addition reaction, but it is also a reduction because you're adding hydrogen to that reactant compound. So let's look at another one. So let's say we had a ring. So let's look at cyclohexene. I can say I had 1,2-dimethyl cyclohexene. Adding hydrogen to that. Since I did platinum there, I'll do palladium. And so these are simply metals from the periodic table. And so to draw that product, again, start by redrawing the compound without the double bond. We don't want to lose any carbon. So we can't take away those methyl groups, but we can go and verify that we do have the correct product. So again, we're only concerned about the carbon atoms where the double bond is located. This top carbon has 4 bonds, no hydrogen. This bottom carbon has 4 bonds, no hydrogen. Look at those same carbon positions. This top bond, 1, 2, 3 bonds, so it has 1 hydrogen. The bottom carbon, 1, 2, 3 bonds, so it also has 1 hydrogen. So going from here, we saw an increase by 2 hydrogen. So that increase in hydrogen represented reduction. It also showed that we have now combined or added this to that compound. And so drawing the product of a hydrogenation reaction, when you're drawing the product of the hydrogenation reaction, simply redraw the compound without that double bond.